Hi, I am interested in taking this situation. You're using a rope to lift a bucket upwards from a well at a steady speed of 3 meters per second, and you raise the bucket 15 meters. And I want to model this situation as thoroughly as I can. I want to use all the representations I can think of to show everything that I know about this motion. So the first thing that I want to do is I want to think about which of our models apply here. Now, I see that it says at a steady speed of 3 meters per second. And so I'm going to take that to mean that the velocity is constant. Since the bucket will be moving upwards the whole time, the direction won't change, the speed won't change. So I must be moving, or the bucket must be moving with a constant velocity. So I can use the constant velocity particle model. Um, I am assuming then that the small moments in time where I make the bucket begin moving, it's got to speed up. I'm going to stop the bucket at the top, so it's got to slow down. So I'm making the assumption that those little changes in motion are small enough that I can ignore them for the big picture motion of that 15 meters. So I've got a constant velocity. Also, if the bucket is being pulled by the rope upwards with a constant velocity, then that seems to me like the forces should be balanced. So the balanced force particle model should also apply since the velocity is not changing. So thinking about what representations can I use then for the constant velocity model, for the balanced force model? I could begin with a motion map. So I'm just going to set down a ruler here and I'm just going to mark off every, let's say I'll mark off every second. So let's say it starts here at 0 seconds. Then I'm just going to make 1 centimeter represent 1 meter. So after 1 second, it's gone 3 meters. After 2 seconds, it's gone 6. And then I just need to go every 3 meters. So that's 0 seconds, 1 second, 2 second, 3 seconds, 4 seconds, and then the fifth dot at 5 seconds. And I want to show that these are all moving at a constant velocity. So I'm going to show arrows moving up that are all meant to be the same length. And after that 5th second, I'm not quite sure, is it still moving? The 5th second is when I'm going to stop it, so I'm not going to put an arrow on that one. But I'm showing a constant velocity with equal length arrows at each dot up until the 5th second. Now I could also draw with the constant velocity model, I know the position versus time graph. X for position, or I could use Y for position since I'm doing vertical positions. Either way, I started at a position of, let's say the bottom of the well down here was maybe this was a height of 0 meters, 3 meters, 6 meters, 9 meters, etc. Then I could start at 0 meters, although it's my number line, I can set it up how I like. But if I want to start at 0 meters, then I can make a straight line because the velocity is always constant and the slope of this graph is the velocity. So there's a straight line that goes up to 15 meters at a time of 5 seconds. So that line always has the exact same slope of 3 meters for each second. If I wanted to make a velocity versus time graph, then my velocity versus time graph is showing that at any time, the velocity was always exactly positive 3 meters for each second. So at 0 seconds, it's 3 meters per second. At 1 second, it's 3 meters per second. At 2 seconds, it's 3 meters per second, all the way up to 5 seconds. So I'm just showing a horizontal line for that. So I've got a motion map, I've got a position versus time graph, I've got a velocity versus time graph. I could write an equation for the position versus time graph. I know, starting with the generic math y equals mx plus b, I've got position equals slope times t plus the starting position. So vertical position y is equal to slope 3 meters for each second times independent variable plus starting position of 0 meters. And of course, writing plus 0 meters is entirely optional. It would be a whole lot simpler if I wanted to, if I just wrote vertical position height equals 3 meters for each second times t as an equation to relate at any time t, here's the vertical position y. So I think that pretty well covers the constant velocity model, but now what about the balanced force model? So I want to start with making an interaction diagram. If I make an interaction diagram, then I'm going to include the bucket, there's earth, a rope, there's me, I'm pulling the rope's pulling me, the rope and the bucket are pulling each other, earth and the bucket. And what I'm really interested in here is thinking about what's happening to the bucket. And I'm thinking the force between the rope and the bucket is what I would call a tension force. The bucket and the earth is a gravitational force. So if I make a free body diagram, then for the bucket, then I should see two forces. On the bucket's free body diagram, there's going to be a gravitational force down by Earth on the bucket. And we've got balanced forces. There are two forces. So there's just one upwards force to balance this one downwards force. So these need to be equal. So I've got an upwards force of a tension by the rope on the bucket. Now I could calculate this gravitational force if I had a mass. Let's say that the mass of that bucket is 10 kilograms, bucket plus its water. So I could even calculate that gravitational force as knowing the strength of Earth's gravitational field, 9.8 newtons for each kilogram, times how many kilograms there are. So times 10 kilograms. If each kilogram has a weight, each mass of 1 kilogram has a weight of 9.8 newtons, then a mass of 10 kilograms has 10 times 9.8, 98 newtons of weight. So that would also mean, if these forces are balanced, that the tension force by the rope on the bucket has to be the same number, 98 newtons, because we know that these two forces are balanced. So there I've written out about as much as I could about the balanced force and constant velocity models.